Hello everyone, and thank you for coming to our session. Today, we are excited to talk about breaking limits, highly isolated and low overhead Wasm containers. Let me quickly introduce ourselves. I'm Soichiro Ueda, a master's student at Kyoto University. My main research interests are in cloud computing and system software.
Hello everyone. My name is Nozaki. I'm first year of my PhD program at the University of Tokyo. My research interest lies in hardware acceleration and system software. Thank you.
We are graduate school students and have an open source project, Muse. This is a special Wasm runtime that runs on a dedicated lightweight VM. Today we will talk about this project and the future of Wasm. Now, let's start with a quick refresher of Wasm. WebAssembly, abbreviated to Wasm, is a kind of binary instruction format. It was initially intended to run on browsers to fasten CPU-intensive JavaScript codes. But it's becoming increasingly popular outside of browsers. Wasm runtimes that run on general OSs, such as Linux or Windows, have emerged. And we can deploy Wasm applications on serverless platforms. And it's deeply related to cloud native. Container toolchains such as Docker and Kubernetes have added support for running Wasm alongside containers. Given this background, let me briefly explain our project. The left side of the slide shows how conventional Wasm runtime executes. A general OS like Linux runs on the machine, and it executes the runtime. Then, a Wasm application runs on it. And please look at the right side. Our Wasm runtime, Muse, is a kind of thin OS kernel that directly runs a single Wasm application. And it only supports Wasm. This approach enables isolated and lightweight Wasm VM. We believe this will play a key role in the widespread adoption of Wasm in cloud native. The rest of this session will cover these topics. First, we will introduce the challenge of adopting Wasm as a type of cloud workloads. Next, we'll deep dive into our Wasm runtime, Muse, and the mechanism of achieving both isolation and low overhead. Finally, we'll discuss the future of our project and where will Wasm in cloud native be heading from our perspective.
So before we dive into the details of Muse, let me introduce WebAssembly and why it is attractive in the context of cloud native. Wasm is a virtual binary instruction format standardized by WC3. It was originally designed for web browsers, but it is also well suited for non-browsers as well. Wasm has some attractive characteristics. First, it is language independent. We can compile Wasm from multiple programming languages like Rust, Go, or Ruby. Second, it is platform independent. Wasm binary doesn't rely on any specific CPU architectures or operating systems, because it is a virtual instruction set. Additionally, Wasm binary is executed in sandbox environment, so access to memory or system resources are restricted. Wasm binaries are executed by Wasm runtime. Since Wasm is a virtual instruction set, the runtime interprets or JIT compile the binary. The runtime creates sandbox for each Wasm. And each Wasm is given its own memory called linear memory from the runtime. And access to outside the linear memory is prohibited. When Wasm binary want to access to host OS or system resources like file system or networking, it makes WASI code. WASI stands for WebAssembly System Interface, and it's like a system code in WebAssembly. When Wasm issues WASI code, the runtime catches the request and completes the request on the host OS. So let's think of WebAssembly in the context of how to manage applications. Traditionally, virtual machines have been used. Above machine and host OS, we use hypervisor in order to isolate VM. And in each VM, there exists guest OS, library, and applications. That means in order to manage applications, developers have to manage from guest OS to applications for each application. Containers are widely used in application development today. Above machine, host OS, and we use container runtime to isolate each container on the same host OS. Compared to VM, developers no longer need to manage guest OS, so container is much more lightweight than VM. And now, WebAssembly is expected to be the next generation of containers. With Wasm, libraries, application and its dependent libraries are built into single Wasm binary together. And this single Wasm binary is very portable to CPUs and operating systems. So compared to containers, Wasm is very portable and has minimum dependencies. So far, we've seen that Wasm is very portable and can be built from multiple programming languages and has minimum dependencies. It sounds like Wasm is a very great candidate for the next format of application delivery or application execution. However, we think it is very important to reflect whether Wasm is really perfect. We think there are still remaining challenges when it comes to using Wasm in public cloud environment. So let's think about the requirements of public cloud. In multi-tenancy situation, workloads from many different users run side by side on the same cloud platform. So there is a risk of malicious workload try to attempt to break out of its boundaries and try to access to cloud platform or other workload. So strong isolation of each workload is very important in public cloud. However, Wasm does not offer efficient isolation itself. This is because Wasm shares the same host OS among multiple workloads. It is often said that Wasm is safe, or Wasm is safe because it is executed in the sandbox environment. This is true as long as everything stays in the sandboxed environment. However, when the Wasm binary wants to access to host resources, in other words, Wasm binary makes WASI call, this assumption breaks down. When a Wasm binary issues a WASI call, it goes through the Wasm runtime, and Wasm runtime completes the request in the host OS. And what is important here is the underlying system, underlying host OS is shared among Wasm applications. So if there is a vulnerability in Wasm runtime, malicious workload can exploit and illegally access the host OS or another workload. This is actually similar with containers because containers share the host OS among containers. This CVE is a vulnerability of handling file descriptors in RunC, and this allows container escape for malicious workloads. Even if we conduct extensive testing of Wasm runtime, unfortunately, we cannot eliminate the risk of vulnerability completely. So in order to use Wasm safely in public clouds, we need more strong isolation. And in this situation, it's common to use hypervisor to isolate workloads and utilize VM-level isolation. By using a hypervisor, we can utilize CPU privilege level to isolate each workload. So let's take a closer look at this software stack which enables VM level isolation. Above machine, host OS, and hypervisor, we run guest OS. And inside the guest OS, Wasm runtime runs WebAssembly application. And we can see a lot of layers stacked in this situation. And what's important here is, if the application is just a single Wasm binary, some of these components are redundant. In particular, a rich guest OS like Linux are often unnecessary. Guest operating systems like Linux are designed to run multiple applications with multiple background services. However, for just running one single Wasm application, these Linux functions are not needed. So we thought about how to reduce the overhead of this guest OS and Wasm runtime. And to the answer of this, we developed Mewz, an operating system for specialized for WebAssembly. And the main feature of Mewz is it is designed for running just one Wasm binary. Unlike general purpose operating systems like Linux, Mewz doesn't have process isolation or context switching, but it has minimum features for running Wasm application like WASI implementation or linear memory management. In this way, Mewz achieved both VM level isolation and minimum guest OS overhead. So let's deep dive into the Mewz. Mewz is an operating system specialized for WebAssembly. As mentioned before, Mewz runs on top of the hypervisor KVM, so it provides VM level isolation. And at the same time, the guest OS of Mewz is designed for running just one application. This design of operating system is referred as unikernel. In this way, Mewz achieves both high isolation by VM and lightweight guest OS. The source code of Mewz is available at this GitHub project, and Mewz is also listed on CNCF landscape project. So from here, let's dive into how Mewz runs WebAssembly and WASI. First, we have a WebAssembly application built from programming languages. Then we use a ahead-of-time compiler to compile Wasm application into ELF file. Here we use our own compiler, Waska. We developed our own compiler instead of using existing compilers because we need to combine Wasm application and operating system. I will explain this later. And then we compile Mewz OS into ELF file. Mewz OS is written in Jig language, so we use Jig compiler for this step. And then we statically link ELF file from Wasm binary and ELF file from Mewz, and we get a kernel image. Here, WASI plays a very crucial role. WASI is a system call in Wasm, and the APIs of WASI is defined in the specification. For example, WASI has an API called fdread. So when the Wasm binary wants to access to file systems, the binary calls fdread. And on the Mewz side, it has the own implementation of fdread. Because of this, we can link wasm.o and mewz.o statically. And this means that Wasm application and Mewz become a single kernel image, and Mewz functions are called just like a normal function calls. That's all how Mewz executes Wasm and WASI binary. So as for performance, we evaluated the performance of HTTP server, and we compared it to the Wasm Wedge. It is a very famous Wasm runtime. we executed both runtime on virtual machines. And Muse achieved 30% performance improvement compared to Wasm Edge. This is because Muse is designed for running just a single Wasm application. So there is very little overhead, both in boot time and execution time. So as for performance, let me briefly touch on this topic. One of the major performance advantages of Muse is it can bypass the system call. Please look at the left side of the slide. This shows a typical case when we run Wasm runtime on hypervisors. When Wasm binary calls WASI call, then the Wasm runtime catches the request and translates the WASI call into system call to the guest OS. And then the guest OS completes the system call by performing context switch. And please look at the right side. This shows how Muse works. As mentioned before, the WASI call and WASI implementation of Muse are combined together during the build time. So the WASI call from Wasm binaries are just like a normal function call in Muse. This is a significant performance advantage because system call and context switches of general operating systems are very expensive. So by avoiding these system calls, Muse achieves much better performance.
And surprisingly, you can launch a Muse instance using Kubernetes. You may have heard the news that Docker and Kubernetes have supported Wasm. What this really means is that container runtimes delegate the execution to Wasm runtimes, which run the Wasm binary found inside the provided OCI image. This is made possible by runwasi, which is a sub-project of Containerd. We have added support to launch Muse using runwasi, though this part of our work is not yet open source. And now, here's the demo. First, it applies a pod manifest. This manifest specifies an HTTP server compiled to Wasm as the image and sets Muse as the runtime. And this action launches a Muse instance as a pod on Kubernetes. As you can see, we can confirm it's running with kubectl get pods, and we can also access the pod using the curl command. Now, let me briefly explain how runwasi works. First, let's look at how a standard container is run. A high-level runtime like Containerd calls a low-level runtime, such as runc. In this relationship, Containerd manages things like container images, while runc is what actually creates the container. Here, runwasi allows Containerd to call a Wasm runtime instead of runc. Runwasi is a kind of library. It allows you to write codes that makes Containerd call any specific Wasm runtime. So what we did was write the code that allows Containerd to launch Muse using the runwasi. It takes the Wasm binary from the container image, links it with Muse to create a kernel image, and then launches a VM to execute it. The simple action of adding a pod to Kubernetes triggers this sequence of events in the background, resulting in running a Muse instance. Now, let's focus on the future outlook for our project. And also, we'd like to talk about the future direction of Wasm from our perspective. As we said earlier, in the context of cloud native, Wasm is often seen as the next evolution of containers. Wasm allows you to package an application as a single binary and deploy it to the cloud like containers. In addition, Wasm has several advantages over containers, such as being more lightweight, more portable, and offering stronger security. So it might seem like Wasm is simply superior to containers. However, do we really need it? Container technology is already mature, and we all are very familiar with it. And moreover, we have already accumulated significant assets in container technology. To migrate to Wasm, we might have to throw them all away. Then, what is the compelling reason to switch from containers to Wasm? To answer that question, let's first recall why we moved from VMs to containers. Containers also have various advantages over VMs. A well-known example is that they are lightweight because they share the host OS kernel. However, we would argue that being lightweight is not the primary reason with container. Rather, we believe the biggest reason is the ability to package applications at low overhead and the comprehensive ecosystem of tools. Think about the container workflow we know. With tools like Docker, we can instantly build an image, pull one from a registry, and run it anywhere. This developer experience is the true power of container technology. This suggests that technology adoption is typically driven by the new capabilities it offers, not just by its non-functional advantages. In other words, the point is about how a technology fundamentally changes our overall experience. Now let's bring the discussion back to Wasm. What new functional capabilities does Wasm provide? And what new use cases does this enable? We believe there are two. The first is component model. It enables components written in different programming languages to call one another. This allows you to use libraries written in other languages and to package your code into units called components. This is a clear distinction from containers. However, it's the second point that we want to focus on. That is portability. We believe that its ability to run across different OSs and CPU architectures is what offers new possibilities. With containers, you have to prepare and manage a separate image for each OSs and CPU architecture. However, a single binary is all you need with Wasm. This characteristic is particularly valuable in IoT and edge computing, because IoT and edge environments often involve diverse OSs and CPU architectures. Wasm's portability is a huge advantage. Moreover, Wasm's lightweight is also a key advantage, especially considering the limited resources of most IoT and edge devices. As a result of these benefits, Wasm adoption in the IoT and edge is increasing. Looking ahead, we believe the next step is for Wasm to be used in environments where the cloud and edge collaborate. And this is the compelling reason we need to choose Wasm over containers. So let's consider running everything on Wasm from the cloud down to the edge and IoT devices. Wasm's portability eliminates the need to create a separate binary for each environment. This allows you to treat your diverse environments in a much more uniform way. Moreover, this could potentially enable us to offload edge processing to the cloud or even perform live migration. As a first step toward this vision, we believe the first thing we need is a platform that can abstract the details of each environment, like cloud and edge. And that's why we are building such a solution using Muse and K3s. K3s is a lightweight Kubernetes distribution for IoT and edge. In our architecture, we manage all resources as K3s worker nodes, whether they are on-premises edge devices or Muse instance in the cloud. This enables us to deploy Wasm workloads uniformly across this entire spectrum. As a result, we can manage our Wasm workloads consistently, regardless of where they are physically running. Furthermore, all of these are connected by a Kubernetes overlay network, and this makes it easy to distribute the load from the edge to the cloud. And this is our vision for a cloud service that can integrate with edge and IoT by using Muse. First, the K3s control plane is running in the cloud. Then, Users connect their on-premises devices to the control plane as workloads. And on the cloud, Muse runs in a nodeless fashion, similar to AWS Fargate. This allows users to manage their local devices using K3s, while also being able to scale out to the cloud with Muse whenever they need. And standard runtime can be used on the edge, while our highly isolated Muse runtime is used in the cloud, and the user doesn't need to be aware of this distinction. The platform intelligently and transparently applies the optimal runtime for the target environment. And we are planning to move this project forward to achieve it. Finally, let's summarize the presentation. Wasm is gaining significant traction for cloud use. However, there are still challenges to using it in the cloud as is. The primary issue is that Wasm's native isolation is insufficient to meet the requirements of multi-tenancy. On the other hand, if we use a virtual machine to isolate Wasm, we lose its key benefit of being lightweight and introduce unnecessary overhead. To solve this, we developed Mewz. It uses a virtual machine to isolate Wasm while keeping the overhead to a minimal. Our approach is to bundle our Wasm application and a specialized OS into a single artifact that runs directly on a hypervisor. Unlike a conventional VM setup, this removes the need for a bulky guest OS like Linux, thus drastically reducing the virtualization overhead. Looking ahead, our project will focus on enhancing the integration between cloud and edge. By leveraging Wasm's portability and lightweightness, along with Muse as our specialized cloud runtime, we are developing a solution for unified workload management. The goal is for this solution to transparently use the optimal runtime for each specific environment. That's all for our presentation. Thank you for listening. We have about 3 minutes left, so do you have any questions?
Thanks for great talk. Sorry if you say in talk, but I'm interested in written by Zig. This layer have Go and Rust ecosystem, very huge, but why choose Zig? Also, there what benefit there was Zig language in this layer?
So, your answer is what programming language is?
Yes.
This is any programming languages that supports Wasm.
Oh.
Yeah.
Means very natively, right?
Such as.
We receive Wasm binary as an input, and this Wasm binary can be built from these programming languages. So.
I see. Thank you.
Thank you very much.
Do you have any questions?
Thank you for a great presentation. I think you said the kernel doesn't have a context switch.
Yes.
And so I'm wondering if you can run like any kind of program. Like for example, I think Nginx like creates a lot of forks. So like that kind of program, can you run?
We've not run such as Nginx, but I think Nginx is I remember someone compiled Nginx to Wasm, but yeah, the code was too old. So yeah, we haven't tried it, but if we can compile Wasm to Nginx, Nginx to Wasm, we could run it on Muse.
So as long as you can compile Wasm, then like you should be able to run the binary.
Yeah,
Okay, thank you.
Thank you. It's time. Yeah. If you have additional questions, please come to us. Thank you for listening.
Thank you very much.